I will give you a question based on electric dipole. You can try to solve this. Deduce an expression for the electric field at a point on the equatorial plane of an electric dipole of length 2a. Basically, this is a derivation. Deduce an expression for the electric field at a point on the equatorial plane of an electric dipole of length 2a. How do we do this? We know what is a dipole. A pair of charges with opposite sign. What will we do is consider an electric dipole AB consisting of two charges plus q and minus q, separated by a distance 2a. We will consider a dipole. Minus q, and then the separation of 2a will have plus q. The distance between them is 2a. So we have to find out the electric field at a point on the equatorial plane. Now let O is the midpoint here. O, and let us say P is the point where we want to find out the electric field, and let us say P is at a distance r from this point O. From O, let us say we want to find out the electric field at point P, and let us say it is at a distance r from O. We have to find electric field at P. Now this is R, so we know the O is the midpoint. This will be A, and this is also A. The total electric field is nothing but the vector sum of electric field due to plus q and the electric field due to minus q. electric field at P due to plus Q as, let me say E plus Q is 1 by 4 pi epsilon naught into Q divided by the square of the distance between the charges. What is the distance between the charge and the point P? So this distance is, from this triangle, I'll mark this point as A and this point as B, because in the beginning I have written consider an electric dipole AB consisting of two charges plus Q and minus Q. I have written from triangle OAP, the length AP is R square plus A square. So Q divided by square of the distance between the charge plus Q and P. Square root of R square plus A square and its square. This will be equal to 1 by 4 pi epsilon naught into Q divided by R square plus A square. Square root square, so they cancel. Half into 2 will become 1. And the direction of this is away from plus Q. So the direction of this field is along AP. If I mark the electric field E plus Q as so this is E plus Q. Similarly, electric field at P due to minus Q charge. E minus Q as 1 by 4 pi epsilon naught into Q divided by, again, the distance between B and P. Distance between P and P. R square plus A square. Square root of square root of R square plus A square whole square. The magnitude is same as E plus Q, but only the direction will change. So I can write E of minus Q as 1 by 4 pi epsilon naught into Q divided by square root of square. So it will become R square plus A square. Along, so it will be towards minus Q, so I can write along PB. If I mark this E minus Q, I will mark E minus Q in this figure. Along PB. So it is towards minus Q. E minus Q. Now net field is the vector sum of EQ and E minus Q. So to find out E plus Q and minus Q vector sum, let us resolve these into horizontal component and vertical component. Now consider E plus Q. Let this angle is theta. Also this angle is theta. Because this angle is theta, the horizontal component of E plus Q and the vertical component we can resolve like this. This is the horizontal component and the vertical component is so this component is E plus Q and it is sin theta. Because this angle is theta, so this angle will also be theta. So vertical component will get E plus Q sin theta and the horizontal component is E minus Q cos theta. Similarly, for E minus Q, you resolve it into two components. We will get two components. One is along line PO. Another one is along E plus Q cos theta itself. Another component is along this itself. We can write this as this is E minus Q sin theta and this is E minus Q cos theta. The vertical component get cancel each other because the magnitudes are equal, so equal and opposite, so they get cancelled. So to find out the net field, we have only the horizontal components. Resultant field, resultant electric field at P can be found by resolving E plus Q and E minus Q into rectangular components into horizontal and vertical components. Remember, the vertical components cancel each other, therefore net field at P is E, which is equal to E plus Q cos theta plus E minus Q cos theta. We know E plus Q is 1 by 4 pi epsilon naught into Q divided by R square plus A square into cos theta plus E minus Q is also the magnitude is same, 1 by 4 pi epsilon naught into Q divided by R square plus A square into cos theta. So this is 2 times 2 divided by 4 pi epsilon naught into Q divided by R square plus A square into cos theta. Now substitute for cos theta. From the figure, cos theta is R, cos theta is A divided by square root of R square plus A square. From the figure, cos theta is A divided by square root of R square plus A square. Substitute and then simplify. Q divided by R square plus A square into A divided by square root of R square plus A square. So let us simplify this. 1 by 4 pi epsilon naught into 2QA divided by R square plus A square to the power half plus 1, that is 3 by 2. For R very greater than A, we get it as E is 1 by 4 pi epsilon naught into 2QA divided by R cube, because R square into 3 by 2, so we will get it as R cube, and we know 2QA is nothing but P. Substituting P equal to Q into 2A, we get net field E is equal to 1 by 4 pi epsilon naught into P divided by R cube. 1 by 4 pi epsilon naught into P by R cube. This is the electric field on the equatorial line of a dipole.